this discussion, we're going to get into looking at above threshold MOSFETs a little bit more into the band picture and a little bit more in terms of where does the actual equations come from. So what you can see on the one side is the sort of definitions for our NFETs and PFETs. And if we define both gate voltage, source voltage, and drain voltage in these forms, we get exactly the same equations, maybe different parameters for both of these two devices, whether it be NFET or PFET. In the NFET, we're looking at voltages coming up from its substrate. In the PFET, we're looking at voltages down from its well or substrate. And so therefore, we define it this way. Now, when you look at a typical equation, we're going to imagine that a couple things are going to be true. We're going to get this interesting quadratic expression. And the first question you might wonder is, like, again, where is this going to come from? We need to think about this carefully. So, returning to sort of the band picture of a MOSFET that you would look at, and this is again talking about a MOSFET starting with the voltage, with the source at ground. The drain is at say VDD, the highest potential, so it keeps it mostly in saturation through the whole region. And then we have the gate voltage is going to sweep from a lower to higher potential. What we're going to find is that the gate voltage itself is going to start by moving this voltage down, but of course it's going to be flat because in subthreshold the current is below the threshold current, which means that the carriers themselves do not actually affect the electrostatics by any significant amount. But as the current goes up, we're going to find both that this starts to pin close to the conduction band where the inversion occurs, and we start getting a drop because the charge in the channel itself, changing the potential and actually changing what happens. As we go down, we're going to get a potential, and then eventually it'll still roll off, meaning that the MOS capacitor went from inversion and then moves its way towards depletion at this edge, and then basically I've got a subthreshold channel the rest of the way, to where I get to the place where it's ohmic and I've got a case where the channel is inverted all the way from one end to the other. Both of those cases are important. Now the question is, what do I have and how do I begin to look at this? So one can go in great depth in this derivation, but I want to kind of initially bring out a couple key points that are going to show up again and again. Now, we're going to find that we get two key terms here. One is the charge of the source, and one is the charge at the drain. And these are actually referring to what is the additional charge beyond where I need to be at threshold in terms of the charge that I'm getting at the source edge and at the drain edge. If you remember that in inversion, we get additional charge at those regions. And so we want to look at those regions of the device, and they're going to actually be one of the charge of the source side and one of the charge of the drain side. So they're going to be a characterization of the MOS capacitor at those endpoints. It's not sufficient to just say, I only have the endpoints. I need to understand what happens in between. But those two things will be very important. Now, one of the first key things to realize is both of these quantities have to be greater than 0 to make any sense of being above threshold, sort of physics. If QS is less than 0, we're very clearly going to be in a subthreshold space. If QD is less than 0, we're in an interesting place where, very much connected with this red curve, where it's going to be inversion for a while, and then at the very back end it becomes subthreshold. And this is where this is going to be a case where QD has to be approaching closer to 0 of at least this approximation. There's still the depletion region charge underneath it that you wouldn't want to ignore in general, but for these calculations it's sufficient because it's usually high enough. So this would actually give me sort of a structure for my quadratic structure. Alright, so now what? So now when I look at the structure, I go, well, how am I going to make sense of this? Well, I know if this is going to be bent downward, my current is going to be by drift. Okay. And so I can talk about drift as being, that current as being mobility times the total charge. You might be used to thinking about this in density and charge density, so it actually works itself out. And then times an electric field. So you might ask, well, how on earth would I solve this? Well, I could start out by saying I got QS and QD. Maybe really qualitatively I could say, let me take the average, right? There's some number, let me take the average number and work with it. So that would be just a sum of this. The second question I could say is, well, what is the electric field? And this is where it's very important to notice is that the charge difference, the charges are related to voltages, and particularly to source and drain voltage, but it would be really, I would actually notice I've got a different voltages in that region. So I might imagine that one way to talk about this is talk about the charges over a dielectric constant, and I could actually eventually get something out that says, yeah, maybe this is where the difference of voltages come from. Difference of voltages over a particular distance is likely to give me something that's like an electric field. Okay. So if I were to think about this just qualitatively, just kind of working through where the math's going to come from, I might imagine that this is going to be, the current will be proportional to the sum of QS plus QD times a multiplication of QS minus QD. And that really will give me a QS squared minus a QD squared. And in fact, if I sort of go with that and sort of say, okay, now there's going to be other constants, particularly some K proportion K, there will also be kappas in here because after all, I still have a MOS capacitor to worry about. I still have coupling of the gate into the system. And so as a result, what I'm going to, I can imagine saying, here's the QS and QD terms. And what I'm going to get from all this is I'm going to get something with kappa VG minus VT, or VT0, and then minus VS on this. And so I get one term there, one term here. Again, kappa VG minus VT, or VT0. And VT0, because it really isn't a threshold voltage, minus VT. And so this is going to be typically the way you would kind of get the basic equation. Now, the one difference is going to be when this QD, as written, would be equal to or less than 0, right? Which means that we're in this red curve region, that really this edge at the drain really is still subthreshold now. It's going to mean I'm going to approximate QD is equal to 0, which means this whole second term is gone. So if I took the equations I have up here, this kind of like the second term just disappears. It basically vanishes. It does not all of a sudden increase and now all of a sudden my current starts becoming negative. Many smart people have made that mistake. That's clearly not what's going on here. It's missing an assumption there. But what we'll get is then a current which is then going to be just the gate voltage and source voltage. There's a kappa on the gate voltage. There is not on the source voltage. So be very careful to not all of a sudden just assume that if I'm in above threshold that these are going to be the same thing. They are not. And the gate voltage and source voltage affect the device in different strengths, both subthreshold and above threshold. So hopefully this structure gives you a good idea of sort of the idea of the overall rough derivation for the above threshold MOSFET. Doing this more carefully requires a bit more work, but certainly can be done. And once you kind of see the intuition of where you're going to go with it, it makes that level derivation much, much easier to comprehend and understand.